Hi everyone, in this video I'll be showcasing my embedded fuel pump system built on an Arduino Mega. This project was designed to demonstrate core embedded systems concepts, including finite state machine architecture, interrupt-driven flow sensing, real-time control, hardware abstraction, and fault handling. The system integrates an OLED display, a matrix keypad, a Hall effect flow sensor, a diaphragm pump, and a MOSFET-based pump driver circuit to simulate the operation of a real fuel dispensing system. I'll walk through the hardware setup, demonstrate the system operation, and explain some of the embedded software architecture and safety features implemented throughout the project. I will now go into a little bit more detail about the hardware setup. The Arduino Mega serves as the main embedded controller running the application state machine and hardware drivers. The OLED display provides real-time system feedback including fuel volume, transaction cost, and system status information. The matrix keypad is used for user input and fuel grade selection, while the trigger button controls active pump operation. For fluid simulation, the system uses a diaphragm water pump controlled through a MOSFET-based driver circuit. This allows the microcontroller to safely switch the higher current load of the pump. The Hall effect flow sensor generates pulse signals as fluid moves through the system, and those pulses are counted using interrupts to calculate fuel volume in real time. I will now walk you through a full transaction using the system. The system starts in the ready state, where it waits for user input before beginning a transaction. Pressing the A key will transition the system into the fuel selection state, where the user can select between regular, premium, and diesel fuel options. Each has a different price. So once the fuel grade is selected, the system enters the active pumping state. In this state, when you hold the trigger button, it will enable the MOSFET driver circuit and power the diaphragm pump. As water flows through the Hall effect flow sensor, pulse signals are generated asynchronously and counted through an interrupt service routine. The firmware will continuously convert those pulse counts into fuel volume and transaction cost in real time, while the OLED display updates continuously with live transaction data. When fueling is stopped and you do not want to fuel anymore, the user can select the B key and the system will transition into the complete state. This displays a summary which includes the total fuel volume, the fuel price, and the total cost. Pressing the A key will reset the system back to the ready state. Next, I'll demonstrate the system's fault handling behavior. In addition to the normal fueling workflow, the firmware includes safety checks to detect abnormal pump operation and transition the system into an error state when needed. One fault condition is no flow detection. While the pump is running, the firmware checks whether the flow sensor pulse count is increasing. If the pump is active but no flow pulses are detected, the system will stop and display a no flow error. This helps protect the system from conditions like a blocked line, disconnected sensor, empty reservoir, or pump running without actual fluid movement. Once the fault is displayed, the pump remains disabled until the user resets the system and returns to the ready state. Overall, this project demonstrates several core embedded systems concepts, including finite state machine architecture, interrupt-driven sensing, real-time control, hardware abstraction, and fault handling. Future improvements could include storing the calibration and fuel pricing settings in EEPROM, designing a custom PCB for the pump driver and sensor interface circuitry, or implementing PWM-based pump speed control. Thank you for watching.